Alright guys, this is going to be a video homework answer key for some select problems. I got a lot of questions on this homework, more than usual, so I thought I would clarify some of the most commonly asked questions on this homework. So for number one, I will post that as a PDF file attached with this, so if you want to check out that proof, I already gave you most of the steps, so I'm sure that one was fine. Alright, but I got a lot of questions on number 2 and 3, so I definitely want to take a look at these two. Alright, so on number 2, if a circle has a radius of 6, what is the length of the chord determined by an arc of 60 degrees? Alright, so I got a circle, radius 6. What is the length of the chord determined by an arc of 60 degrees? So what I'm starting with is a 60 degree arc. So I could draw that arc anywhere, right? 60 degrees is about 1/6 of a circle, so let's say that's 60 degrees. And I want the length of the arc, sorry, not of the arc, I want the length of the chord determined by this arc. So if there's my arc, here is the chord determined by that arc. And I'm going to call that x, and that's the length we are looking for. So if I draw in my radii, boom, boom, right, I know my radii are 6 centimeters, or 6 doesn't tell us units, they're 6 units each. And if this arc is 60 degrees, then that means my central angle that intercepts that arc is also 60 degrees. I can see this is an isosceles triangle, right, because I have two congruent legs, which means these base angles also must be congruent, and hopefully you can see that they're going to be 60 and 60. So this isosceles triangle is in fact equilateral, which makes our missing side length 6. Alright, for number 2, I think I meant to type in 270 for this one, but doesn't really matter. If I have 260 degrees, let's say from there to there, that's 180, and then I go 80 more degrees, so that's almost a full quarter of a circle, right? It's almost 270 degrees, but it was 260. So there is our arc, 260 degrees. I just drew in the chord. Let's call the chord, we can call it AB. Let's say it has a length of x, right? So major arc AB has a measure of 260 degrees, which means minor arc AB, well, they have to add up to 360. So this minor arc here, right, that's going to be 100 degrees, which means when I draw in my central angle here, this would also have to be 100 degrees. And again, this is 6 and 6. This will be isosceles triangle, which means our base angles will be, well, 40 and 40, right, to add up to 180. Let me get rid of that degree symbol, looks like too many zeros. And right, from here, plenty of ways to solve for x. If you want, you could do right triangle trig by drawing in the height or altitude, right, making two congruent triangles. What else could I do? You could do law of cosines, I guess. Easiest way I see though is definitely law of sines. So let's do law of sines. We can say that the sine of 100 degrees over x is equal to the sine of 40 degrees over 6, right? And just cross multiply to solve for x. I actually don't have the calculation handy, but that is how you would solve for x here. And again, I'm sorry I didn't tell you what to round to, so just round to the nearest tenth, and I'll have that answer in the posted PDF. Alright, number 3. Find the length of a chord whose shortest distance is 3 centimeters from the center of a circle whose radius measures 5 cm. So here's the center of the circle. We have some chord. I have no idea where to draw it, but I'm just going to draw it there. And the shortest distance from the chord to the center is 3 cm. So we know the shortest distance between a segment and a segment and a point, right, is the perpendicular that passes through that point to the line. So that's the shortest distance, and this distance here, that's 3 centimeters. And we know our radius, what was that? Circle of radius 5 centimeters, so these are 5 centimeters each. And we're looking for the length of this chord. Let's call that x again. So from here, I see right triangles. We can probably do some right triangle trigonometry. And actually, we can just use Pythagorean theorem, right, to solve for these lengths here. We can call this x over 2, I could call it y. But very simply, I see it is a 3, 4, 5 Pythagorean triplet. So that means that's 4. This is also 4, which means x has a length of 8 here. So the length of the chord is going to be 8 centimeters. Alright, number 4, in a circle with radius 10, the measure of arc AB is 90 degrees. Alright, so let me draw in arc AB. Alright, that's a quadrant, 90 degrees. So here's my center. I can draw a right angle in. This arc has a measure of 90 degrees. We have a radius of 10. And again, we're looking for the length of the chord. This is an isosceles right triangle, which means this is a 45, 45, 90 right triangle. So hopefully you see why we did trig and special right triangles in a unit before this, because it comes up all the time, right, in doing this problem. Even over here, we had to use law of sines. So now that we have these skills, I know it's x radical 2 for the hypotenuse, so this is a 10, 10, 10 radical 2 right triangle. You can also use Pythagorean theorem, of course, but the length of AB is going to be 10 radical 2. Right, find the distance of AB from the center of the circle. Should probably label this AB, but again, the shortest distance is going to be the perpendicular, right, to the chord. And let's call that x. So this is 90 degrees. You could do law of sines again, but it's a right triangle, so I'm just going to use right triangle trigonometry. Or I can even just use Pythagorean theorem. I think I'll use Pythagorean theorem. So if I draw in one of those triangles for a right angle, here's the center. All right, let's call that center O. I'm drawing out this triangle with that being A, and this point being, I guess I'll call that C. All right, so in this triangle, this length AC here, right, that's going to be half of 10 radical 2. So that'll be 5 radical 2. These were both 45-degree angles, and we're looking for the length of OC with a hypotenuse of 10. So there is so many ways you can solve for x here. Right triangle trig, law of sines. You can use law of cosines if, I don't know why you would do that. But I'm just going to use Pythagorean theorem again. I'll just use x squared plus 5 radical 2 squared equals 10 squared. Get some practice with radicals. We haven't done that in a while. So x squared plus 5 radical 2 times 5 radical 2. 5 times 5 is 25. Rad 2 times rad 2 is 2. So 25 times 2 is 50. And that's going to equal... Oh, what the heck am I doing? It's isosceles, right triangle. These two legs are going to be congruent, of course. So I better get 5 radical 2. But let me finish it up. So x squared is equal to 50. X is equal to the square root of 50. Square root of 50 is 25 and 2, right? Square root of 25 times square root of 2, which is, of course, 5 radical 2. So I just wasted a whole bunch of time not realizing it was isosceles, but of course, the distance is going to be 5 radical 2. All right. Good stuff there. 5 and 6. If a square is inscribed within a circle, so here's a circle. If I got a actually I want those tick marks. Actually they go away, so never mind. but we got a square in here. Alright, I don't need to make this perfect. You got a square in here, center. Alright, that's going to be a right angle. Right, a square is a rhombus, right? Remember, properties of a rhombus, their diagonals are perpendicular to one another. So, there we go, that's 90 degrees. Find the measure of the minor arc intercepted by one of its sides. So here's one side of the square. The measure of the intercepted arc, right, is going to be the same as the measure of the central angle, which intercepts that arc. So that's 90 degrees. Right, if it asks for the major arc, that would be this guy, and of course that would be 270 degrees. And number 6, same idea. Now we got a pentagon, so 5 sides. So this might be a little hard to draw, but I'll try my best. 1, 2, 3, 4, 5. So what's a measure of a central angle in a pentagon? So you might be thinking sum of interior angles, the n minus 2 times 180 formula, but it's easier than that, right? Central angle, well, I know that full angle, right? That's 360 degrees. If you draw in all the triangles, right, we have 1, 2, 3, 4, 5 congruent angles. So I'm just going to do 360 divided by 5. And 360 divided by 5, what does that equal to? 20, 60, 70, 72 degrees. So if that's 72 degrees, measure of one of the arcs intercepted by one of the sides, also 72 degrees. Alright, number 7, if concentric circles with center O have radii as marked, determine whether the statements given are true or false. The measure of angle BOD equals the measure of angle AOC. Yes, of course, those are the same angle, just different ways to name them. That is true. The measure of arc AC is the same as the measure of arc BD. Right, the measure of them is the same. Yes, that is true. Right, they are both however many degrees because it has the same central angle. Right, so the measurements are the same, but what's not the same is the lengths of them are not the same, right? We can't say the length of AC equals the length of BD, right? That's false. And that's really what C is saying, is AC congruent to BD. Of course they're not congruent, they are not equal in length, so that one is false, right? And that, of course, is also false. That's not equal. Right, so again, 2 ways to measure an arc. You can measure the length of an arc, right? Or you can also say measure an arc by its number of degrees. So that's it. If you still have any questions, just let me know. But this will also be posted as a PDF on Classroom. All right. Hope you guys are staying safe, and hope you and your families are well. See you guys later.